Okay, so by now you should have completed the graphing calculator investigation, looking at various different polynomial functions, and you were asked to list different things about those graphs, including the number of roots and the end behavior. And the goal of that investigation was to have you start to notice some of the patterns that occur within different types of polynomial functions. So in particular, what will the end behavior be given the degree of the function, as well as how many roots will it have, and so on and so forth. So I was hoping that you would have noticed from that investigation that functions with odd degree, so your linear, cubic, and quintic functions, kind of behave similarly. So for all of those ones that you graphed, the end behavior was always either quadrant 3 to quadrant 1, as we have here on your note, or from quadrant 2 to quadrant 4. If you didn't notice that, go ahead and have a look at that investigation again, and you'll see that those were the only two choices for end behavior for all of the functions that had degree 1, 3, or 5. Now, what determines whether it will be from quadrant 3 to quadrant 1 or from quadrant 2 to quadrant 4? To determine that, we need to look at what we call the leading coefficient, and I've given you a definition for that term at the top of your note. So the leading coefficient is the coefficient of the term with the largest exponent. So for example, the leading coefficient of f of x right here is -2. Basically, for functions with odd degree, if the leading coefficient is positive, then the graph will extend from quadrant 3 to quadrant 1. And to help you remember that, always remember what the line with a positive leading coefficient does. So the line y equals x, in other words, extends from quadrant 3 to quadrant 1. And similarly, when the leading coefficient is negative, think of the line with, or any line really, with negative slope. So a line with negative slope has end behavior from quadrant 2 to quadrant 4. And similarly, any function with odd degree will behave that way if the leading coefficient is negative. Okay, now for functions with even degree, we want to compare those ones to parabola. So a parabola would be the easiest function we could think of that has even degree. And if a parabola has a positive leading coefficient, so a positive a value, we know that it opens up, which makes the end behavior quadrant 2 to quadrant 1. Every function with even degree that has a positive leading coefficient will have end behavior from quadrant 2 to quadrant 1. And when the leading coefficient is negative, the graph extends from quadrant 3 to quadrant 4, just like the graph of a parabola with a negative leading coefficient does. Okay, so when the leading coefficient is negative, the graph extends from quadrant 3 to quadrant 4. Next thing I was hoping you would notice was in the number of roots column on your investigation. So the maximum number of roots is equal to the degree of the function. So if you go back and look through, for the functions with degree, say, 5, the maximum number of x-intercepts you could have would be 5. Now that doesn't necessarily mean they have 5, but the most you could have is the degree of the function. So the maximum number of x-intercepts of a cubic function is 3. Now, in terms of minimum number of roots, we could say that functions of odd degree have at least one root. Functions of even degree do not necessarily have any roots at all. So for example, you could have a parabola that has its vertex above the x-axis and opens up. That would have no roots. But for functions of odd degree, because your end behavior is always either quadrant 3 to quadrant 1, or from quadrant 2 to quadrant 4, you're always crossing the x-axis. So functions with odd degree will always have at least one root. And those were the main points that I was hoping you would get from that investigation. But if you have any questions about it, please let me know, okay, before you get started on the homework. And that's all for now.